Hey folks, my name is Nathan Johnston. Welcome to lecture 16 of Vector Calculus, which is all about Green's theorem. And actually the next several lecture videos are going to be all about Green's theorem because there's a lot to say about the theorem and there's a lot to do with it. So in this video, we're just going to introduce it, okay? I'm going to show you the statement of the theorem and we're going to play around with just the hypotheses and the statement of it to try to understand what it's telling us. And we'll do our very first computational example, okay? But then we're going to break at that point and then we'll have more videos where we come back, do more computational examples and see sort of some of the neat stuff that we can do with it. And then eventually at the end of this week, we're going to finally prove it. Okay, but let's start off with just what is Green's theorem, okay? And it's a really neat tool that it relates to different types of integrals that you've seen at this point, okay? It's going to relate double integrals, which remember, double integrals, they're a tool for multivariable calculus that tell you how to compute volumes, or maybe more specifically, signed volumes. If you've got a region in two-dimensional space, then when you do an integral over that region, you get a volume under a surface above that region. Okay, and what Green's theorem does is it relates that to another type of integral that we've seen, a vector line integral, the type of integral that we learned about last week, just a couple lecture videos ago. Okay, so here's what the theorem says. Suppose that you're in two-dimensional space and you've got some closed and bounded region D in two-dimensional space. Okay, what we're going to do is we're going to give a name to the boundary of that region. So that's all this notation here means. Okay, this funny little curly D followed by the big D, that just means the boundary of D. That's what this curve C is. Okay, and this boundary, it's going to consist of finitely many simple closed piecewise C1 curves. Okay, that's a mouthful. We're going to talk about these hypotheses in a second. For now, the way to think about all these hypotheses is just, well, D is a region that is reasonably nice, and the boundary of that region is also reasonably nice, okay? So that's all we care about, is they've got to be sort of well-behaved shapes, okay? And we'll pin down exactly what that means in a minute, okay? And you've got some vector field from the domain D to R2, okay? And the only restriction on that is it's got to be C1. So when I take derivatives of its entries, I get continuous functions. Okay, well, the theorem says if I parameterize the boundary, if I parameterize C so that when I walk, along that parameterization, when I walk along the curve specified in the direction specified by that parameterization, then D is on the left. If I walk along the curve in that way, then the vector line integral along that curve is equal to the double integral of the region of this function here, of the partial derivative of the second component of the vector field with respect to x, minus the partial derivative of the first component of the vector field with respect to y. Okay, so I realize that's a ridiculously big mouthful. Let's try to break this down and talk about all the little bits and pieces of it, and then we'll sort of play around and do actual numerics with it. Okay, so first off, some notes on notation and just terminology and stuff here. So first thing to be aware of is Green's theorem is very much specific to two-dimensional stuff, okay? Like D needs to be a two-dimensional region. It lives in R2. This vector field acts on R2, okay? The vectors live inside R2. They're two-dimensional vectors. Okay, it's a two-dimensional specific thing, and I point this out because this is very different from all of the earlier stuff that we've done in this course. Earlier in the course, everything that we've seen previous to this works in any number of dimensions. Like usually we visualize it in 2 and 3 dimensions, but really like all that previous stuff, scalar line integrals, vector line integrals, dot products, yada, 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 all that stuff that we looked at earlier in this course works in any number of dimensions. This is breaking that pattern, okay? It's for two-dimensional stuff only, okay? There are going to be versions of this theorem that we see for higher dimensions, but we're not there yet. Okay, so because it's two dimensions only, it makes sense to give names to the two entries of the vector field, okay? So let's call the first entry F1, that's a scalar field, this F1. And the second entry is F2, that's also a scalar field. So that's these two functions here that we're taking partial derivatives of. Those are just the two entries of our vector field. Okay, and another note on just notation here, okay, on the left here, this vector line integral, you might be wondering why the heck there's this little circle here, and that's just signifying to us that we're doing a vector line integral around a closed loop. In other words, like the curve that we're integrating around, it's not just a path like this from one point to another. No, it comes back and ends where it started. It's a closed loop, and we just use this notation here to sort of remind ourselves of that, because as we go on, sort of the distinction between integrals over closed loops and non-closed loops is going to be important to us. So it's useful to have that built into the notation. And another point that I want to make is if you remember back to the previous lecture video, oftentimes we write vector line integrals in differential form, and this is what it looks like over here, okay? So like another way that you'll often see Green's theorem phrased is as saying, okay, well, this vector line integral equals this double integral. That's another way to say the exact same thing because these two notations here just mean the same thing as each other, okay? They're just different notations for the same thing. Let's talk about what types of regions you can use in Green's theorem, okay? So let's break down the different hypotheses that we saw in Green's theorem up above, okay? So first off, it said that the region D that you're integrating over in the double integral, it's got to be closed, okay? And what that means is it's got to include its boundary. Whichever points are right on the edge of that set, they've got to be in the set, okay? Also, another hypothesis that was given was that that region, it's got to be bounded, okay? And all that means is probably what you would expect that to mean is it doesn't go off to infinity in any of the directions, okay? It's not shooting off that way forever in any direction, okay? Or another way of saying this is it fits inside of some circle, right? You could draw a circle, maybe a huge circle, but still, there's some circle you can draw around it. If you can, then it's bounded. If you can't, it's not bounded, okay? Next up, what about its boundary? Okay, there are also lots of conditions on the boundary curve of the region D. So this curve C. Okay, well, first off, it's got to be closed. And what we mean by that, closure of a loop means that the loop comes back to where it started. Okay, so it's not just like a curve that goes from one spot to another. No, it comes back to where it started. It's a closed loop. Okay, it's got to be simple as well. Okay, and what simple means for curves is that they don't cross themselves, okay? So you don't have a curve that's sort of, it's going along and then comes back and at a different time it crosses itself like that. Like, no, that's not allowed for the boundary of the region, okay? It's got to be a simple curve, no self-crossings. Okay, so let's look at some regions that, Green's theorem is fine with and some regions that Green's theorem is not fine with. So over here, on the left here, yeah, okay, so this region D that's highlighted in yellow, okay, it's closed because it includes its boundary curve. When I do solid lines like this, I mean including that curve. It's bounded because I can draw a circle around it, okay? Its boundary curve is closed, right? If you keep tracing it out, you come back to where you start, and it's simple, it doesn't cross itself or anything like that. So this region here, yeah, that's fine. The second region, this is actually fine as well. Okay, this region here, maybe feels a little bit icky because it's got a hole in it, but that's okay. Like these two boundary curves taken together, the outside and the inside, those together make up the boundary curve C. Okay, still satisfies all the hypotheses. Okay, this region, this yellow set here, D, it's still closed. It's still bounded. It fits inside some circle and the boundary is closed, okay? It comes back to where it starts, and, it's simple, like it never crosses itself, okay? And maybe I'll go back up to the statement of the theorem here to remind you, okay? So, like, the boundary, it just has to consist of finitely many curves with all these properties. So this particular boundary, it's consisting of two curves with these properties, okay? And that's fine. Like, there can be even more holes in this set, and it's still going to satisfy all the hypotheses. You can still do Green's theorem on it. It's fine. Okay, for some examples of things that are not fine, maybe consider this rightmost one first. Okay, this set here, if I include the boundary, yay, it's closed. It's not bounded, okay? There's no circle that I can draw around this because, these arrows here, they're meant to indicate that it just goes up and up and up and up in those directions. If it does something like that, no, it's not bounded. You can't do Green's theorem on it. Don't try. All right, for another example of region that does not satisfy these hypotheses, consider this thing here, where what I mean by this is, okay, it's everything inside this square, except not including the things on this diagonal here, okay? So it includes everything sort of in this triangular region up here and this triangular region down here, but not on sort of that infinitely thin line going between them. Okay, Green's theorem doesn't apply here because that region there is not closed, okay? If I were to sort of compute the closure of it, I'd end up getting the points on this diagonal line as well, okay? And then I could apply Green's theorem, and if I did it to that region, then the boundary is just this outside shape. If I tried to do it to this region, then the boundary includes this sort of inner diagonal as well, and things could go kind of haywire, okay? So you need to make sure that you've got a closed region if you're going to be doing Green's theorem, okay? All right, one final thing that we have to talk about before we can go on and do actual computations with this, and that is I want to clarify one part of the theorem where we said that we're going to parameterize the boundary curve C so that D, the region, is on the left. So why do we have to do that? I've been trying to say over the past couple of weeks that when you do scalar and vector line integrals, it doesn't matter how you parameterize. And now I'm saying that it does. You got to parameterize specifically so that the region's on the left. So what gives? Okay, so let's talk about this. For scalar line integrals, that's still true. For scalar line integrals, it never matters how you parameterize the curve. It's just you're always going to get the same thing, okay? The formula for scalar line integrals, it does not depend on the parameterization that you use, other than the fact that, the parameterization has got to be C1 so that, okay, first off, you have derivatives, so you can sort of compute the speed of the path, and those derivatives have to be continuous so that the integral plays nicely. Okay, but other than that, other than the fact that you have to pick a continuously differentiable parameterization, it doesn't matter if you pick this parameterization x or if you pick a different one y that traces out the same curve, the scalar line integral is going to be the same. So anything that you can do with one, you can do with the other. Okay, vector line integrals, more or less that's true. For vector line integrals, the vector line integral that you get, it almost doesn't depend on the parameterization, except it kind of does. There's one detail that matters, and that's what we call the orientation of the parameterization. It's which way the particle is going, okay? If you've got, like, for example, if you've got two endpoints of your curve, is the particle going from this one to this one, or is it going from this one to this one as time increases? And that aspect of the parameterization matters. Speed doesn't matter. It doesn't matter if the particle is going really slow then really fast, or if it has constant speed the whole time. You'll still get the same vector line integral regardless. But orientation matters. It matters if it's going like forwards or backwards. And this makes some sort of sense, right? I would expect that vector line integrals depend on the orientation of the parameterization. Because, like, for example, in this vector line integral down here, if we integrate along this path, remember what's happening is I'm sort of measuring how much the path is going in the same direction as the vector field and accumulating that over the curve. Okay, so over here, I mean, the path is going more or less in the same direction as the vector field. Here, it's going kind of backwards from the vector field. But then over here, it's going with the vector field again. And it sort of looks to me that there's probably more positive contributions there than negative. So I think probably this vector line integral is positive overall. Okay. Whereas this one, where now the particle is going the other way, well, like this time the path is going in the opposite direction of the vector field. It's moving against the wind, so to speak. Down here it's going with it, but now it's going against it again. Okay, this time I think probably the negative contributions went out. This vector line integral on the right, I would expect probably is negative. Okay, the path is typically moving opposite to the vector field. Okay, so the relationship between these two vector line integrals here is they're just negatives of each other, okay? And that happens in general. Okay, if you're doing a vector line integral, but then you change, the orientation of your path, of your parameterization, if you reverse the direction of the particle, you're just going to give a negative sign to your vector line integral. But other than that, it's not going to change, okay? The speed at which the particle is moving along the path doesn't matter. If it goes faster or slower, doesn't matter. It's not going to change anything. But the orientation might give you an extra minus sign. And that's why when we do Green's theorem, we need to be specific about which way we're going around the boundary. And that's just convention that we choose the direction that keeps the region on the left, okay? That's just a convenient choice. People have stuck with it, okay? So it's usually the way Green's theorem is phrased. We didn't have to make that choice. It's arbitrary, but it's nice to be consistent. If you wanted to, you could phrase Green's theorem like this, okay? So all the same hypotheses, okay? So a nice closed bounded region, the border curves or the boundary curves are nice, C1, yada, yada, yada. But this time we're going to parameterize the boundary so that D is on the right when we walk around that boundary. All that would change is now the vector line integral is going to be the negative of the expression that we saw before. Okay, so we just get an extra negative sign. Before we would have del f2 by del x minus del f1 by del y. This time we just got them in the other order. We've got del f1 by del y minus del f2 by del x. Okay. So I mean, it doesn't matter which way you do it, but with the region on the left is sort of the typical way to do it. So that's what we'll stick with, just for consistency's sake. All right, good times. So let's actually, I don't know, play around with Green's theorem and let's do a computation here. Okay, so suppose that D, it's in R2 because Green's theorem has to be in R2. Suppose D is some region. It's in the first quadrant. It's bounded by the line y equals x and the parabola y equals x squared. And what we're going to do is we're going to verify Green's theorem for a particular choice of vector field over this region. Okay, so our vector field is f of xy equals xy y squared. What we're going to do is we're going to compute both halves of Green's theorem. We're going to compute the double integral over this region, and we're going to see that we get the same thing as if we compute the vector line integral around the theorem, just so that we're all on the same page and make sure that we understand what Green's theorem is saying. Okay. Alrighty, so let's do this, okay? So we've got two things to compute. Let's maybe start with the double integral. Let's compute that, okay? So before we do that, I'd better know what my region looks like. Okay, so I draw the line y equals x, and there it is. Draw the parabola y equals x squared, and there it is. And it's the region between those two curves in the first quadrant. So it's this yellow region right here, okay, between those two curves. The points of intersection are 0, 0, and 1, 1. And what we're going to do is we're going to compute the double integral over that region of this scalar field, right? This del f2 by del x minus del f1 by del y, that's just a scalar field. It's a thing that we learned how to integrate back in multivariable calculus, okay? So we go to our vector field here. We say, okay, this y squared, that's my f2. I do the x partial derivative of it, and oh, that's just 0. Next up, I need my f1, that's xy here, the first entry of my vector field, and I just do the y partial derivative of it, so xy just becomes an x. Okay, so that's the function that I'm going to be double integrating. Okay, what are the bounds on my integral? Okay, so this is just stuff from multivariable calculus. You already know how to do this. What are the bounds on my integral? I could do x first, then y, as was suggested up here. I'm going to flip it around so that I do y first, then x, just because I already sort of have the problem phrased in that way, right? Like if I ask, okay, what's y going from? Well, y is going from the bottom curve, which is y equals x squared, up to the top curve, which is y equals x. Okay, so those are my inner bounds of integration. My y bounds of integration, y is going from x squared up to x. Okay, and then what's x going from on the outside? Well, it's going from x equals 0 to x equals 1. So those are my x bounds of integration. And now I just compute this iterated integral, right? Okay, so minus x integrate with respect to y becomes negative xy. Okay, the bounds are y equals x squared up to x. I plug those in. I get negative x times this y with the bounds plugged in, which becomes x minus x squared, right? This x minus that x squared. And I'm just going to simplify that a little bit, multiply it out. Negative x times negative x squared becomes a positive x cubed. Negative x times x becomes a negative x squared. And now I just do the next integral, right? Now I'm done the y integral, I just do the outer x integral now, and x cubed becomes an x to the 4 over 4, x squared becomes an x cubed over 3. Plug in your endpoints, you're just going to get a quarter minus a third, which negative a 12th, right? Find the common denominator, and you get negative 1 over 12 as the value of that double integral. Okay, fine and dandy. Let's verify Green's theorem in this case. In other words, we've computed one half of it. Let's compute the other half. Let's compute the vector line integral that's suggested here and see that we get negative a 12th for that as well. Okay, so what is the vector line integral? Well, first off, we've got parameterize the boundary curve, right? I need, a path that traces this out and then traces that out. Okay, so I'm going to trace out the two different sides here one at a time individually. Okay, so that parabolic piece, not too hard. I'm just going to parameterize it by t squared, right? Because my x component, I'm just going to call that t, and then my y component, I'm going to call it, it's x squared, so it's t squared. And x is just going from 0 to 1, so t is going from 0 to 1 as well, because t is x. Okay, so that's a fine and dandy parameterization of the parabolic sort of lower side of that region. I also need a parameterization of the line at the top here. And your first guess might be, well, maybe I'll just use the parameterization, my path is tt, right? Because x is t, y is t, and that'll take me up that line of slope 1. And that works, except it's going in the wrong direction. Right? Remember that you want to parameterize it so that, like, if I was to walk along here, I keep the region on the left as I walk along. Like, imagine you're a person walking along this curve. You want your left arm hanging into this yellow region here. Okay, so I've got to parameterize it so that for small t, I'm up here at 1, 1, and for large t, I'm down here at 0, 0. So I'm just going to parameterize it via 1 minus t, 1 minus t, because now when t is 0, I'm up at the top right point, 1, 1, and when t is 1, I'm down at the bottom left point, 0, 0. So now I'm going so that d is on my left. Okay, and now all I do is I do that vector line integral. Integrating over c, well, it's integrate along the parabolic arc plus integrate along the line segment. Just add those two contributions together. Okay, and now for this, you just plug everything in. Okay, what is my vector field f? I'll just scroll back up to the question up here. My vector field is xy, y squared. Okay, so all I do for this first one, here's my x, here's my y. So x times y is t cubed, and y squared in the second entry is going to be t squared squared, which becomes t to the power 4. Okay, and then this f prime, the velocity vector, just compute the derivative of f itself. So t becomes 1, t squared becomes 2t, and I get that over there. And do the same thing for the second integral now, okay? Vector field applied to this path. So again, the first entry of my vector field is x times y, so 1 minus t times 1 minus t. The second entry of my vector field was y squared, so 1 minus t squared is the second entry. And then velocity vector g prime, just take the derivative of each entry, you get -1, -1, so the vector -1, -1. Okay, now I compute a couple dot products. Okay, so dot product over here, I'm going to get t cubed plus 2t to the power 5. Over here, I'm going to get 1 minus t squared times -1 plus 1 minus t squared times another -1. Oh, that's just -2 times 1 minus t squared. And now this is just a single variable integral. You know how to do these. It's a little bit tedious, but whatever. You know how to do it. The first integral works out to 7/12. The second integral works out to -2/3. And when you add those up, you get -1/12, just like we got before. Okay, so yeah, Green's theorem works in that particular case. The vector line integral around the boundary is the same thing as the double integral inside the boundary. Okay, and that's all we're going to do today. Okay, we'll leave it there. In the upcoming lectures, we'll see what neat things we can do with Green's theorems. For example, sometimes we'll be able to compute volumes or areas via vector line integrals, but also vice versa. We're going to be able to compute vector line integrals by finding out, areas and volumes. So it provides a really neat bridge between these two different types of integrals that we've seen. All right, but we'll leave it there. See you next time, everyone. Have a good couple days.